by now you've seen the anomaly detection algorithm, and we've also talked about how to evaluate an anomaly detection algorithm. It turns out that when you're applying anomaly detection, one of the things that has a huge effect on how well it does is what features you use or what features you choose to give the anomaly detection algorithm. So in this video, what I'd like to do is say a few words, give some suggestions and guidelines for how to go about designing or selecting features to give to your anomaly detection algorithm. In our anomaly detection algorithm, one of the things we did was model the features using this sort of Gaussian distribution with, xi giving mu I, comma, sigma squared I, let's say. And so one of the things I often do will be to plot the data or plot a histogram of the data to make sure that the data actually looks vaguely Gaussian before feeding it to my anomaly detection algorithm. And it will usually work okay even if your data isn't Gaussian, but it's sort of a nice sanity check to run. But by the way, in case the data looks non-Gaussian, the algorithm will often work just fine. But concretely, if I plot the data like this, and it looks like a histogram like this, and the way to plot a histogram is to use the HIST or the HIST command in Octave. But it looks like this. This looks vaguely Gaussian, so if my features look like this, I'd be pretty happy feeding it to my algorithm. But if I were to plot a histogram of my data, and if it were to look like this, well, this doesn't look at all like a bell-shaped curve, right? This is a very asymmetric distribution. It has a peak way off to one side. If this is what my data looks like, what I'll often do is play with different transformations of the data in order to make it look more Gaussian. And again, the algorithm will usually work okay even if you don't, but if you use these transformations to make your data more Gaussian, it might work a bit better. So given a data set that looks like this, what I might do is say take a log transformation of the data, and if I do that and replot the histogram, what I end up with in this particular example is a histogram that looks like this. And this looks much more Gaussian, right? This looks much more like the classic bell-shaped curve that we can fit with some mean and some variance parameter sigma. So what I mean by taking the log transform is really that if I have some feature x1 and then the histogram of x1 looks like this, then I might take my feature x1 and replace it with log of x1, and this is my new x1 that I plotted the histogram of on the right. This looks much more Gaussian. And rather than just a log transform, some other things you could do might be, let's say I have a different feature x2, maybe I replace that with log x plus 1, or more generally with log x, maybe that's x2, plus some constant c, and this constant could be something that I play with to try to make it look as Gaussian as possible. Or for a different feature x3, maybe I replace it with x3, I might take the square root. Square root is just x3 to the power of 1/2, right? And this 1/2 is another example of a parameter I can play with. So I might have x4, maybe I'll instead replace that with x4 to the power of something else, maybe to the power of 1/3. And all of these, this exponent parameter or the c parameter, all of these are examples of parameters you can play with in order to make your data look a little bit more Gaussian. So let me show you a live demo of how I'd actually go about playing around with my data to make it look more Gaussian. So I have already loaded into Octave here a set of features x. So I have 1,000 examples loaded over there. So let's plot a histogram of my data. I'm going to use the histx command. So there's my histogram. By default, I think this uses 10 bins in histogram, but I want to see a more fine-grained histogram. So I'm going to use hist of x comma 50. So this plots it in 50 different bins. Okay, that looks better. Now, this doesn't look very Gaussian, does it? So let's start playing around with the data. Let's try hist of x to the 0.5. So I'm going to take the square root of the data and plot that histogram. And okay, it looks a little bit more Gaussian, but not quite there. So let's play with the 0.5 parameter. Let me set this to 0.2. Looks a little bit more Gaussian. Let's reduce a little bit more. 0.1. Yeah, that looks pretty good. I could actually just use 0.1. Well, let's reduce it to 0.05. And okay, this looks pretty Gaussian. So I could define a new feature, which is x new equals x element-wise exponentiation into the 0.05, and now my new feature x new looks more Gaussian than my previous one, and I might instead use this new feature to feed into my anomaly detection algorithm. And of course, there's more than one way to do this. You could also have hist of log of x. That's another example of a transformation you could use. And that also looks pretty Gaussian, so I could also define x new equals log of x, and that would be another pretty good choice of feature to use. So to summarize, if you plot a histogram of the data and find that it looks pretty non-Gaussian, it's worth playing around a little bit with different transformations like these to see if you can make your data look a little bit more Gaussian before you feed it to your learning algorithm. Although even if you don't, it might work okay, but I usually do take this step. Now, the second thing I want to talk about is how do you come up with features for an anomaly detection algorithm? And the way I often do so is via an error analysis procedure. So what I mean by that is this is really similar to the error analysis procedure that we had for supervised learning, where we would train a complete algorithm and run the algorithm on a cross-validation set and look at the examples it gets wrong and see if we can come up with extra features to help the algorithm do better on the examples that it got wrong in the cross-validation set. So let's look through let's try to reason through an example of this process. In anomaly detection, we're hoping that P of x will be large for the normal examples and it'll be small for the anomalous examples. And so a pretty common problem would be if P of x is comparable, maybe both are large for both the normal and the anomalous examples. Let's look at a specific example of that. Let's say that this is my unlabeled data. So here I have just one feature x1, and so I'm going to fit a Gaussian to this, and maybe my Gaussian that fit to my data looks like that. And now, let's say I have an anomalous example. Let's say my anomalous example takes on an x value of 2.5. So I'm going to plot my anomalous example there. And it's kind of buried in the middle of a bunch of normal examples. And so this anomalous example that I've drawn in green, it gets a pretty high probability, right? It's the height of the blue curve. And the algorithm fails to flag this as an anomalous example. Now, if this were maybe aircraft engine manufacturing or something, what I would do is I would actually look at my training examples and look at what went wrong with that particular aircraft engine and see if looking at that example can inspire me to come up with a new feature x2 that helps to distinguish between this bad example compared to the rest of my red examples, compared to all of my normal aircraft engines. And if I manage to do so, the hope would be then that if I can create a new feature x2, so that when I replot my data, if I take all my normal examples, like my training set, hopefully I find that all my training examples are these red crosses here, and hopefully if I find that for my anomalous example, the feature x2 takes on a very unusual value. So for my green example here, this anomaly, right, my x1 value is still 2.5, but maybe my x2 value, hopefully it takes on a very large value, like 3.5 over there, or a very small value. But now, if I model my data, I'll find that my anomaly detection algorithm gives high probability, to data in the central region, slightly lower probability to that, slightly lower probability to that, an example, and then an example that's all the way out there, my algorithm will now give very low probability to. And so the process of this is really, look at the mistakes that it's making, look at the anomaly that the algorithm is failing to flag, and see if that inspires you to create some new feature. So find something unusual about that aircraft engine and use that to create a new feature, so that with this new feature, it becomes easier to distinguish the anomalies from your good examples. And so that's the process of error analysis and using that to create new features for anomaly detection. Finally, let me share with you my thinking on how I usually go about choosing features for anomaly detection. So usually, the way I think about choosing features is I want to choose features that might take on either very, very large values or very, very small values for examples that I think might turn out to be anomalies. So let's use our example again of monitoring the computers in a data center. And so with lots of machines, maybe thousands or tens of thousands of machines in a data center, and we want to know if one of the machines, one of our computers, is acting up, to doing something strange. So here are examples of features we might choose, right? Maybe a memory use, number of disk accesses, CPU load, network traffic. But now let's say that I suspect one of the failure cases, let's say that in my data set, I think that CPU load and network traffic tend to grow linearly with each other. Maybe I'm running a bunch of web servers, and so if one of my servers is serving a lot of users, I'll have a very high CPU load and I'll have a very high network traffic. But let's say I have a suspicion that one of the failure cases is if one of my computers has a job that gets stuck in some infinite loop. So if I think one of the failure cases is one of the machines, one of my web server code gets stuck in some infinite loop, and so the CPU load grows, but the network traffic doesn't, because it's just spinning its wheels and doing a lot of CPU work, stuck in some infinite loop. In that case, to detect that type of anomaly, I might create a new feature, X5, which might be CPU load divided by network traffic. And so here, X5 will take on an unusually large value if one of the machines has a very large CPU load but not that much network traffic. And so this will be a feature that will help your anomaly detection capture a certain type of anomaly. And you can also get creative and come up with other features as well. Like maybe I have a feature X6 that's CPU load squared divided by network traffic. And this would be another variant of a feature like X5 to try to capture anomalies where one of your machines has a very high CPU load but maybe doesn't have a commensurately large network traffic. And by creating features like these, you can start to capture anomalies that correspond to particular unusual combinations of values of the features. So in this video, we talked about how to take a feature and maybe transform it a little bit so that it becomes a bit more Gaussian before feeding into an anomaly detection algorithm, and also the error analysis in this process of creating features to try to capture different types of anomalies. And with these sorts of guidelines, hopefully that will help you to choose good features to give to your anomaly detection algorithm to help it capture all sorts of anomalies.